So the emission spectra of the elements drive us to the conclusion that energies in the atoms are quantized. But why? What is different between the ground state and the excited states of an atom? In 1913, the Danish physicist Niels Bohr took the idea of quantized energy levels and combined it with the Rydberg equation to come up with an energy level diagram for hydrogen. The Bohr model of the atom was the first in which the motion, and therefore the energies of the atom, were assumed to be quantized. In this context, quantized means they are not continuous, but can only be at certain values. This is somewhat like being on an elevator. While you can be in transit between floors, you only stop at the first, second, third floor, etc., never in between. Unlike stops in an elevator, though, the energies of an atom are not evenly spaced. The model Bohr developed was based on the known energies of the lines in the hydrogen spectrum. We saw earlier that the energies could be modeled by this equation. We've also seen that the energy of the photons give the energy difference between levels. In mathematics, a difference is represented by subtraction. If we distribute the constants inside the brackets, we arrive at what appears to be the difference between two similar terms. Bohr reasoned that the energy of each level must then follow this equation. As before, Z is the charge on the nucleus, which is the same as the atomic number. H and R sub h are constants, while n is a positive integer. Note that while all the terms on the right-hand side are positive, there is a negative sign in the equation, meaning that all of the energies in this model are negative. As before, the lowest energy state will be the most negative. Let's evaluate the energies for hydrogen. There is one proton in the nucleus, so Z equals 1 for hydrogen. Ground state, or lowest energy state, will occur when n equals 1. If both Z and n are 1, the energy will be negative HR. We can plot this on a one-dimensional energy scale, where 0 energy is at the top. The energy of the n equals 1 ground state is then at the bottom. For n equal 2, the energy would be negative HR over 4. This should only be 1/4 of the way down from the top. We draw it not quite to scale here. Notice that the energy values we would calculate for other elements would be different, because Z would be different for other elements. For n equal 3, the energy would be negative HR over 9. For n equals 4, the energy is negative HR over 16. Notice that the energy levels get closer together as we go up. We can add energy levels for n equal 5 and 6 to the picture as well. One of the reasons the Bohr model was accepted almost 100 years ago is that if you actually calculate the difference between energy levels, you will find that they correspond almost exactly with the lines that appear in the spectrum of hydrogen. In the visible portion of the hydrogen spectrum, the emission lines correspond going from upper levels to the n equal 2 level. The reason we don't use the Bohr model today is that it only works for chemical species with one electron. Atoms and ions with more than one electron have spectra with more lines than can be accounted for with the Bohr model.